Hi, I would like to do an explanation about the red-black tree. In a video I made with Hui-Chi about how databases work, I briefly described how red-black trees work. Here I want to talk more specifically about how the tree balancing mechanism works in the red-black tree. I'm going to assume that you know the basics of how a binary search tree works. If you don't know that, by all means, you can go study that at your leisure, and then you can come back and watch this. I want to go over quickly the definition of a red-black tree. There's basically 5 rules that a red-black tree must satisfy for it to be a valid red-black tree. Number 1, every node is either red or black. Number 2, the root is always black. And number 3, leaves are considered black. Number 4, if a node is red, then both its children must be black. That's a very important one. It's a signal for the algorithm to know when something needs to be done to sort of maintain the balance of the tree. And then finally, for each node, all simple paths from the node to the descendant leaves contain the same number of black nodes. I'm going to show a diagram from the book. Every node is either red or black. In this book, it's either black or gray. Gray is red. So we can see that every node is either black or red. The root is black, so we can see that right away. The root is black. Every leaf is, they call that nil. In programming language, you might call that nil or null. We consider those black. If a node is red, then both of its children must be black. So if you pick any red node like 17, both of its children are black. We can see that. Finally, for number 5, if you pick any node in the tree, say, let's pick the root node, then traversing from the root node to the leaf on every path, and you count the number of black nodes encountered, you'll get the same number. So 1, 2, 3, 4. From the root traversing down to the leaf, we got 4 black nodes. 1, 2, 3, 4 again. 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 So that's what they mean when they say for each node of the tree, all simple paths from the node to the descendant leaves contain the same number of black nodes. And that is a important property of the red-black tree because it intuitively sort of maintains that the tree is more or less balanced. There isn't any like section of the tree that's extremely sparse. How do you do red-black tree insertion? To do it, you follow a standard set of procedures. Step number 1 is you use the standard binary search tree algorithm to insert the node in its rightful place. Step number 2 is you color the new node red. And then step number 3 is you're going to check whether you have a conflict. Let's say we wanted to insert the 3 into the tree as an example. So 3 should go here, but step number 2 says color the new node red. So rule number 4, it says if a node is red, then both its children are black. We have created a conflict with rule number 4 in that there is a child of a red node, namely 2, that is also red. So if the parent is red, we'll need to fix it. How are we going to fix it? It depends. And it depends a lot on what our uncle looks like. So who's our uncle? Well, if number 3, that is me, then the uncle of the new node, me, is going to be this guy. That's our uncle. We'll call this guy our parent, and we'll call this guy our grandparent. And sometimes I'm going to use these abbreviations. So P for parent, GP for grandparent, and U for uncle, and perhaps M for me. Okay, these are the salient actors in the various scenarios regarding how to fix up a tree. Okay, so we're gonna say if parent is red, we're gonna check the uncle's color. If uncle is also red, then we're gonna do a color switch. We'll set both of my parent and my uncle's colors to black. Because if we set these guys to black, then that fixes rule number 4 that says the child of a red node must be red. We're also going to change our grandparent to red. And then after that, we're also going to repeat that process, pretending that I am my grandparent. So go back to step 3. So I colored my grandparents' color to be red, and I'm going back. I'm pretending that I am my grandparent now, and I'm going back to step 3 to use the same logic to treat the grandparent. I'll call this case A. That's actually the more simple case. Case B is more complex because case B actually splits up into 4 separate cases. Starting with if my uncle is the right child, or whether the uncle is the left child or the right child of the grandparent, that comes into play a lot, and whether I am the left child or the right child of my parent, that comes into play as well. If my uncle is a left child, and if I am a left child, then we do a certain thing. But if my uncle is a left child and I'm a right child, then there's another thing to be done. I'll fill in what those things are a little bit later. And then if my uncle is right child, and then if I am the left child, there's this thing to be done. And if I am the right child in this branch, there's another thing to be done. And then at the end, we're going to change our parent to black and change our grandparent to red. Okay, and then finally we do the same thing here. We pretend that I am my grandparent, and then we go back to step 3. Of course, if my grandparent does not exist, as in we've topped out the tree, then there's nothing to be done. We can write these nested if statements in terms of a matrix. Uncle can be either the left child or the right child of my grandfather. And then as for me, I can be either the left child or the right child of my parent. Based on where you are within this matrix, there's a set of instructions that you're going to do. So if we're in the left situation, as in my uncle is the left child of my grandparent, and I'm the left child of my parent, then what we're going to do is we're going to right rotate our parent. Right means right rotate. We'll talk about what those mean in just a bit. And L means left rotate. So if we're in the LL situation, we're first going to right rotate our parent, and then we're going to left rotate our grandparent. RL situation, our uncle is a right child and I am a left child, then we're going to right rotate the grandparent. If we're in the LR situation, uncle is left child and I am a right child, then we're gonna left rotate our grandparent. And if we're in the RR situation, my uncle is a right child and I am a right child, then we're gonna first left rotate our parent, and then we're gonna right rotate our grandparent. So this is the procedure. So I'm gonna fill these in here. And basically, this is the procedure for inserting a new node into RedBlack tree. And if you implement this procedure, it will guarantee that the binary search tree will be balanced. Just to give you an idea of how one of these works. So let's start with the LL scenario where the uncle is a left child and I am also a left child. So in that case, let's have the grandparent here. And because my uncle is a left child, uncle goes here, and that means my parent goes here. My parent is the right child. And I am a left child as well, so that puts me here. I'll also put my sibling to the right of my parent. As for what are the children of my uncle, I don't know, and I don't think that matters too much in this case. So based on this rule, first we're going to rotate our parent to the right, and then we're going to rotate our grandparent to the left. So if we want to rotate the parent to the right, we want the parent to go this way. What we want to do is actually replace the parent with its left child. Okay, so what ends up happening when you do this is the left child ends up being the parent, and then the parent ends up being the child of the child. So that's what happens here. If there happens to be a child, so let me say I'll call this my right child here. My former right child will now be the left child of the parent, and but my left child will stay with me. There's this sort of restructuring. Previously, it had this shape here, but after the rotation, it's almost like flipped from left to right, and that's what we're going for. But the parent of me is now the grandparent. The grandparent is now my direct parent, and then to the left of the grandparent has not changed. It's still uncle. This is the result of the right rotation of the parent, which results in the parent getting demoted and me getting promoted. But after this right rotation of the parent, then we're going to do a left rotation on the grandparent. So let's do that. Do another transition process where we're going to left rotate our grandparent. So what does that mean? Well, that means we're going to do a left rotate of the grandparent. And if you want to do a left rotate, that means taking your right child and replacing yourself in the tree with your right child. And in this case, that again is me. Me will actually end up being at the root of the tree. Like me gets promoted, and then grandparent actually becomes my left child. And then the uncle stays with the grandparent. That does not change. But the right child of the grandparent is now going to be my left child, because I yielded my left child to take on the grandparent, and now I have no left child. My left child has to go somewhere, and my left child goes with the grandparent, but my right child remains, and that is my previous parent. My previous right child is now with the left child of my previous parent, and my sibling stays with my previous parent. So we end up with this structure, which, as you can see, looks quite a bit more balanced than we started with. That's what happens if we have the LL case. Now let's see what happens with the LR case. And I'm not going to do these two cases because these two cases are the same as these, just in reverse. So let's do the LR case. Our uncle is a left child, is the left child of the grandparent, and that means our parent is the right child, and I am the right child of my parent. So me, that's me, and then my sibling is over here, and I don't care about what children are on my uncle, so this, as this entry in the table instructs us to do, what we're gonna do, we only have to do one rotation procedure, and the procedure is left rotate of the grandparent, and that's that guy. So we want to left rotate the grandparent, which means it's in that direction. And again, the way you do left rotate is you take your right child and replace yourself with it. So what's going to end up happening is P is going to end up being the root of the node. The grandparent becomes the left child of P. Uncle will stay with the grandparent. To the right of P is me. Now, where does my sibling go? Well, my sibling previously was the left child of P, but now the left child of P has been taken up by the grandparent. But by moving the grandparent to the left, now grandparent's right link frees up. So that's precisely where we're going to place my sibling. So this is what happens when you do a left rotation. This is a program that I wrote in C++. I have implemented the RedBlack tree insert algorithm here is the tree insert function. There's this tree insert fixup function which is in charge of fixing the conflicts in the event that one arises, as I've described. I have this function which tests the insertion of a number of entries, 15 in total. These are names of personalities in a chess event called the PogChamps chess tournament. This code goes through this array of names and inserts each one with a numerical ID as the key into this RedBlack tree. I did a run of this code with the fixup procedure call commented out, and then did another run of it with this fixup put back in. I used the GraphWiz tool to generate visualizations of the tree, which I'm going to show you right now. Okay, we're going to start with the no-fix version, which is essentially equivalent to what a normal binary search tree insert would have done. Every single insert is sort of documented here. At the very beginning, where we just had one node, it looked like this, and then we insert another one, it looks like this, insert another one, looks like this, and so forth. And this is the situation that Hui-Chi was describing in my video with her about how databases work. The problem with binary search trees is if you insert the values in order, you're going to get this very, very long tree that just fans into one direction. And this is as good as a linked list. You don't get the benefit of log insertion time algorithm. Let's see what the tree is going to look like when we actually activate the fix up procedure. This is initial, there's no node, and then we add Hafu as the first node of the tree. So we inserted XQC into the tree, and in this case, no fix-up was necessary, so the final state is the same as the state before the fix-up. Then we're going to insert another node into the tree, Forsen. This step, this is what the tree looked like before the fix-up procedure. As you can see, we have a conflict here, violates rule number 4 that says a red node can only have black children. So what it does is kicks off a fix-up procedure that involves left rotating Hafu. So this is the matrix. In this case, Forsen is the right child. So Forsen is me. I am Forsen. So I'm the right child, whereas my uncle should be the imaginary left child of Hafu. So this guy is my uncle. Even though he doesn't exist, it doesn't matter. We still choose the procedure the same way. Whereas this guy is me, Forsen. I'm Forsen. So because my imaginary uncle is a left child and I am a right child, we're gonna pick L are that procedure which says that I should left rotate my grandparent, which is Hafu. So we're going to left rotate Hafu. I have documented the procedure in the name of the image. So this is left rotate Hafu, and this is the result of left rotating Hafu, which is from here to here. So you want to left rotate somebody. You do that by taking your right child and replacing yourself with it. And then you become the left child of your right child, which is really weird, but that's what it is. So we're going to sever this relationship and then say my right child is now my parent. So what we ended up with is XQC is now the root of the tree, and then we have Hafu as the left child of XQC. Next, we're going to add another node in the tree. This time is Cutie Cinderella. Cutie Cinderella got added as the right child of Forsen, and we have a conflict. We have a red-red parent-child relationship conflict. So we're going to need to fix it up. The first step was, in this case, was recoloring was triggered because Cutie Cinderella's uncle, which is Hafu, is red. And whenever your uncle is red, you have to recolor both your uncle and your parent to be black. And also you have to recolor your grandparent to be the opposite color, which is red. So we just fix that conflict, and we sort of propagated potentially the problem upwards in the tree. And now we're going to pretend we are the grandparent, in this case XQC. So I'm going to pretend to be my grandparent now and check if the coloring of this node red has caused additional red-red conflicts. And in this case, no. However, as final step of the procedure, I forgot to write that down. Sorry, I forgot to write the final step of the procedure is the root of the tree always gets colored black at the end of the entire procedure. And it's actually okay for a black node to have children that are also black node. That's totally allowed. And if we double check if this satisfies all properties of red-black tree, rule number 4 clearly satisfied because the only red node doesn't have any children. But the rule that says starting from any node of the tree, if you walk to the leaf, you should encounter the same number of black nodes. That is true here. So if you start here and then you walk here, there's 2 black nodes. If you walk this way, also 2 black nodes. So this is a valid red-black tree, and a black node is allowed to have black nodes as its children as well. Okay, next we're going to add Ludwig. He got added as the right child of Cutie Cinderella, and now we have a red-red conflict. This time we do not do a recoloring. We do not do a recoloring when your uncle is not red. If your uncle is red, then you do the recoloring, but in this case your uncle is black, so you do not do the recoloring. And instead of doing a recoloring, you go to this table here, and that says am I a left child or a right child? I'm a right child and my uncle is a left child, so we should do this one. Left rotate the grandparent. This is me, I'm Ludwig, and my grandparent is Forsen. So I should left rotate Forsen. And left rotate Forsen means we're going to go this way. So we're replacing Forsen with Cutie Cinderella. Forsen is going to end up being the child of Cutie Cinderella. So this gives us that. And that's the final state of this insertion. We inserted Hikaru. This Hikaru's uncle, which is Forsen, is red, so we do a recoloring. And then now, after doing this fix up, now we're gonna pretend me is my grandparent and redo this procedure, and we check our uncle, but we don't have an uncle. We don't even have a grandparent. So the fix up stops here. There's nothing else to be done, and this is still a valid red-black tree. Okay, and now we're gonna add Alex to this tree. Alex got added here as a child of Hikaru, and then we're gonna check to see whether there's an uncle. There isn't an uncle that is red, so because of that, we do not do a recoloring. And again, we consult this table. Say, okay, my uncle is a left child and I am a right child. Again, we're gonna do a left rotate on my grandparent, which is Ludwig. And that gets us that. Ludwig got demoted and Hikaru got promoted in place of where Ludwig used to be. Now we're gonna insert Andrea. Andrea got added because we're inserting these notes in order, as in we first inserted 1 and then we inserted 2 and then we inserted 3 and then we inserted 4, etc. Everything got added to the rightmost position in the tree. And so there are actually some of these variations that are not getting hit, and I might use a randomized way of inserting them so that the double rotations actually get hit, and I can show you what that looks like. But here is actually a key moment. So Andrea gets inserted here, and we're gonna check the uncle of Andrea, which is Ludwig, and see what color he is. Well, he is a red note, which means we need to do recoloring. We need to color Ludwig and Alex to black. That happened, and Hikaru flipped to red. And now we're gonna say do the same thing while pretending that I am Hikaru, and we're gonna check whether the uncle of Hikaru is red. It's not, which means we're gonna consult this table again. It ends up that we do a left rotate on XQC, which is the root of the note, because XQC is the grandparent of Hikaru. We again chose this rule here from this table, and the result of the left rotate of XQC resulted in this tree, which is looking a lot more balanced now. As you can see, whenever the tree starts looking like it's unbalanced, the next couple of steps kind of restores it into being more balanced. And this is the final state of this tree. At this point, it's actually getting kind of unbalanced, but with time, if you add more entries to it, I'm sure it'll get to be more balanced. Let me do a randomized order of insertion of these chess personalities so that when I run this code, they'll actually hit a double rotation case. At the end of step 6, we had this tree. Forsen was added here. This is the state of the tree before the fix-up procedure. As you can see, there's a conflict here, and because the uncle of Forsen is red, we're gonna do the recoloring, which propagates the red upwards in the tree, and now we have to do the fix-up me as Forsen. And now again we have a red-red conflict here. Now propagating up the tree, our uncle is not red, so we don't have to do yet another coloring. And now we go to the rotation. The rotation table says here that I'm Forsen, I'm actually the left child of Agamator, and Hafu is the left child of Hikaru. So this is a left-left in this table. So this is what we pick. We first right rotate our parent, and our parent is Agamator, so we're gonna right rotate Agamator, and then we're gonna left rotate our grandparent, which is Hikaru. That's what we're gonna do as predicted. First we right rotate Agamator. Agamator is trying to go this way to the right, and you do that by replacing yourself with your left child. So Forsen gets promoted, Agamator gets demoted, like that. And then we're gonna left rotate Hikaru from this state here, which means Hikaru is gonna get demoted now, and Forsen is gonna get promoted into the root of the tree. And at the end, this is what we have. And as you can see, this is a much more balanced tree. Okay, so I hope that gives you a better intuition of how the red-black tree keeps itself balanced. Thank you for watching.